Step outside tonight and look up at the darkest patch of the sky. You might think you're staring at the present moment, watching the stars exactly as they are right now. But you're actually looking into a deep abyss of the past. The light reaching your eyes from the edges of those distant shadows started its journey long before anyone on this planet was even born. What you see is already gone, swallowed by a gravitational grip so intense that not even a single photon could escape. You're staring at a ghost of the cosmos, a frozen memory of a monster that has already changed the fabric of space itself. That comforting darkness above you isn't empty space at all. It's a graveyard of collapsed stars, and you're just seeing the delayed echo of their violent end. For decades, these monstrous entities have been portrayed as nothing more than cosmic vacuum cleaners, endlessly swallowing planets and stars in their path. We've been taught to fear them as the ultimate destruction, a one-way ticket to absolute nothingness, a place where time itself comes to a crushing halt. But that simple, dramatic picture hides a far more terrifying and profound reality, one that challenges the very foundation of our scientific understanding and threatens to unravel the laws of quantum physics. Today you'll find out what black holes really are, and why they might be permanently deleting information from the universe, creating a paradox that keeps physicists awake at night. Before we set off into the dark, I have one question for you. Where in the world are you watching the sky from, and what time is it where you are? Tell us in the comments below. If you love wandering through the night sky, subscribe to the channel. That's what keeps this work going. Let's begin the descent. To understand what a black hole really is, we first have to look at how physicists convinced themselves that such a monster could never exist. If you travel back in time to the 18th and 19th centuries, you will find a scientific community that is completely at peace with the universe. Isaac Newton's laws of universal gravitation have conquered the cosmos. You can use his elegant equations to predict the exact path of a cannonball, the rhythm of the ocean tides, and the precise orbits of the planets. The universe is viewed as a giant, predictable clockwork mechanism. Stars are simply bright, burning spheres of gas forever shining in the dark. Gravity is a gentle, invisible tether that keeps everything in perfect balance. Physicists look up at the night sky and see a wonderfully solved puzzle. Every equation balances perfectly. Everything is resolved. You're taught in every university that nature is orderly, rational, and well-behaved. But in 1784, an English natural philosopher named John Michel, and independently in 1796, a French mathematician named Pierre-Simon Laplace, ask a very dangerous question. They apply Newton's laws to the absolute extreme. Every planet and star has an escape velocity. This is the exact speed you need to travel to break free from its gravitational pull. Think of it like trying to jump out of a deep well. On Earth, the well is shallow enough that a powerful rocket can climb out. On a heavier planet like Jupiter, the well is much deeper, and you need a vastly more powerful engine. But Michel and Laplace ask, what if the well is so incredibly deep, and the wall so perfectly steep that even the fastest thing in the universe, a beam of light, cannot climb out? They theorize the existence of objects they call dark stars. These would be massive bodies whose gravitational pull is so intense that light itself cannot escape their surface. If you were to look at one, you would see absolutely nothing. It would be a perfectly black void in the sky. However, the scientific community quickly dismisses the idea. At the time, light is widely believed to be a massless wave, completely unaffected by gravity. The concept of a dark star is brushed aside as a mere mathematical curiosity, an impossible phantom that has no place in reality. The dogma survives. The universe remains safe. Fast forward to the early 20th century. The comforting Newtonian clockwork is permanently shattered. In 1915, Albert Einstein presents his general theory of relativity, completely rewriting our understanding of the cosmos. Gravity is no longer an invisible pulling force. Instead, it is the curving and warping of space and time by mass. To visualize this, Imagine placing a heavy bowling ball in the center of a stretched, elastic trampoline. The fabric sags heavily, creating a deep, curved dip in the center. If you roll a small glass marble across the fabric, it does not travel in a straight line. Its path curves downward toward the heavier ball, forced to follow the warped shape of the surface. Einstein proves that stars and planets warp the invisible, three-dimensional fabric of the universe in the exact same way. Gravity is not a rope pulling you down, it is the slide you're already falling down. The scientific community is utterly mesmerized. The equations are beautiful, elegant, and seemingly flawless. They perfectly predict the subtle, unexplained wobble in the orbit of the planet Mercury, a mystery that had baffled astronomers for decades. A new, even more perfect dogma is established. The cosmos is finally understood on a fundamental level. There are no dark stars, there are no monsters. Then comes the year 1916. The First World War is violently ravaging the continent of Europe, tearing nations apart in a brutal stalemate. Enter Karl Schwarzschild, a brilliant German astrophysicist and director of the Astrophysical Observatory in Potsdam. He's not sitting in a comfortable, quiet university office surrounded by books and chalkboards. He is stationed as an artillery lieutenant in the freezing, mud-filled trenches of the Russian front. Artillery shells explode around him constantly, shaking the earth. The noise is deafening. The conditions are horrific, unsanitary, and utterly bleak. Worse, he is suffering from pemphigus, a rare, agonizing autoimmune skin disease triggered by the brutal conditions of the front. His body is covered in painful blisters. He is slowly, agonizingly dying in the mud. Yet, amidst this unimaginable slaughter, his mind is fixed on the stars. He is calculating. Working by the faint light of the trenches, he manages to do what Einstein himself thought would take many years to achieve. Schwarzschild finds the very first exact mathematical solution to the impossibly complex equations of general relativity. He perfectly calculates the gravitational field around a single, non-rotating spherical mass. He sends his handwritten manuscript directly to Einstein, a pure beacon of intellect emerging from the absolute hell of war. Einstein is deeply impressed. The math is undeniably correct. But Schwarzschild's elegant solution holds a terrifying, dark secret buried deep within the numbers. The equations reveal a catastrophic limit. They show that if you take any mass and compress it down to a specific, highly critical size, a boundary we now call the Schwarzschild radius, the curvature of space and time does not just dip like our trampoline. The fabric of reality plunges downward infinitely. The curvature becomes so extreme that it creates a definitive boundary in space. We call this boundary the event horizon. It is a point of no return. Imagine a river waterfall where the water flows faster and faster as it approaches the edge. There is a specific point, a line in the water, where the current becomes faster than any fish can possibly swim. Once a fish crosses that invisible line, no matter how hard it fights, no matter how much energy it burns, it is doomed to go over the edge. The event horizon is that exact line in space. If you cross this boundary, the required escape velocity completely surpasses the speed of light. Because nothing in the universe can travel faster than light, absolutely nothing can ever escape. Not a rock, not a spaceship, not a single photon of radiation, and not a single piece of information. Schwarzschild has mathematically proven that the dark stars of Michel and Laplace are not just curious fantasies. They are a direct, inescapable consequence of Einstein's own masterpiece. The monster is real, and it is hiding in the math. The reaction is visceral. The scientific establishment recoils in absolute horror. This solution implies that a collapsing star will shrink down to a point of infinite density and zero volume. We call this terrifying point a singularity. It is a place where the laws of physics simply break down and cease to exist. Nature cannot possibly allow this. Einstein reads the implications of the solution. He accepts the flawless math, but he fiercely, stubbornly rejects the physical reality of it. He hates the idea of a singularity. He believes it violates every core principle of a rational, predictable universe. By 1939, Einstein publishes passionate, highly detailed papers declaring that such a total gravitational collapse is physically impossible. He insists that nature will always intervene, that some unknown outward pressure will always halt the collapse before a singularity can form. He tries to kill the monster once and for all, and yet, the very same year Einstein tried to bury the concept forever, another team of physicists proved that the nightmare was entirely real. That horrifying mathematical truth only becomes real once you understand the brutal life cycle of a dying star. Let us visualize this cosmic laboratory. Picture a star vastly larger than our own sun, suspended in the freezing vacuum of deep space. Inside the core of this massive sphere, a delicate, invisible war has been raging for millions of years. On one side, you have the crushing, relentless inward pull of the star's own immense gravity. It acts like a giant, tightening fist, constantly trying to squeeze the entire star down to a single point. On the other side, you have the ferocious outward push of nuclear fusion. Trillions of atoms are smashing together every second, igniting a continuous thermonuclear explosion that pushes back against the crushing fist of gravity. For millions of years, this titanic struggle is a perfect, elegant tie. The star remains stable, burning brightly, holding its shape against the dark. But this precarious balance cannot last forever, or eventually, inevitably, the star burns through all of its available nuclear fuel. The thermonuclear furnace sputters and finally goes cold. The outward pressure instantly drops to zero. In that terrifying microsecond, the tie is broken. The giant crushing hand of gravity immediately wins the war. With absolutely nothing left to hold up the colossal weight of the outer layers, the entire star begins to fall inward on itself. Imagine trillions of tons of superheated plasma accelerating toward the center at an unimaginable fraction of the speed of light. The core is violently crushed. Atoms are shredded into pieces. So, electrons and protons are violently smashed together to form a solid ball of neutrons. But if the star is massive enough, even the fundamental structural integrity of neutrons cannot withstand the pressure. The collapse becomes a runaway train. In 1939, Robert Oppenheimer and his brilliant student Hartland Snyder publish a groundbreaking paper in the Physical Review, so they mathematically map out exactly what happens during this catastrophic failure. They prove that the star does not just shrink into a dense solid ball and stop. It continues to fall inward on itself infinitely. As the star becomes smaller and smaller, its gravitational pull on its own surface becomes stronger and stronger. The escape velocity at its surface begins to climb exponentially. Finally, the star shrinks past its critical Schwarzschild radius. The escape velocity violently surpasses the speed of light. At that exact moment, the collapsing star cuts itself off from the rest of the observable universe entirely. It leaves behind nothing but a perfect spherical shadow. Oppenheimer and Snyder successfully proved that Schwarzschild's math was not just a strange glitch. It is the ultimate, inescapable destiny of the universe's most massive stars. Ironically, their paper is published on September 1st, 1939, the very day Hitler invades Poland, igniting the Second World War. So, the world's attention violently shifts from the theoretical death of stars to the very real death of nations. Oppenheimer himself is soon called away to the deserts of New Mexico to lead the Manhattan Project, building the first atomic bomb. The study of black holes is largely abandoned, left to gather dust in library archives for nearly 2 decades. Fast forward to the tense geopolitical climate of the 1960s. The Cold War is raging not just between armies, but between the sharpest scientific minds on either side of the Iron Curtain. In the Soviet Union, prominent physicists like Yakov Zeldovich refer to these collapsed objects as frozen stars. Why? Because according to the strange counterintuitive rules of Einstein's relativity, if you were to watch a star collapse from a safe distance, you would see time itself drastically slow down near the intense gravity of the event horizon. From your outside perspective, the collapse would appear to slow to a crawl and eventually freeze in time. The image of the dying star would eternally hover just above the edge of oblivion, slowly fading to red. Meanwhile, in the United States, a highly prominent theoretical physicist named John Archibald Wheeler seeks a more evocative term to capture the public imagination. During a pivotal scientific conference in 1968, he popularizes the term black hole. The name is a masterpiece of scientific branding. It immediately sticks. It captures the terrifying absolute finality of the concept perfectly. The idea officially transitions from an obscure, highly contested mathematical footnote into a global pop culture phenomenon, yet a lingering doubt remains. Critics still desperately argue that perhaps Oppenheimer's mathematical model is just too perfect, too perfectly symmetrical. What if a star isn't a perfect sphere when it collapses? What if it's spinning wildly or heavily deformed by a nearby companion? Surely nature would find a chaotic way to avoid forming a true, infinitely dense singularity. In 1965, a brilliant British mathematician and physicist named Roger Penrose completely destroys this last shred of hope. Using entirely new, highly advanced topological math, he does not just calculate the collapse of a perfect sphere. He tackles the messy, chaotic reality of a real star. Penrose delivers a rigorous, crushing proof. No matter what shape the star is, or how chaotic the collapse may be, once an event horizon forms, the trapped matter has absolutely no choice but to continue falling inward. It must inevitably crush down into a point of infinite density. A singularity is not a mathematical artifact, it is physically unavoidable. This brilliant, undisputed proof will later earn him the Nobel Prize in Physics. The decades-long scientific war is over. The existence of black holes is no longer a subject of polite academic debate. It is a solid, terrifying, undeniable fact of nature. The historical crisis seems entirely resolved. The scientific community finally accepts that black holes exist, and they are the ultimate cosmic tombs. They are the final resting place of matter, absolute one-way streets where everything that falls in is trapped in darkness forever. But this apparent resolution secretly gives birth to a much larger, much more terrifying puzzle. Enter Stephen Hawking in the year 1974. A brilliant, fiercely determined theoretical physicist confined to a wheelchair at Cambridge University, he decides to do something no one else had seriously dared to attempt. He sets out to combine the two great highly incompatible pillars of modern physics, the physics of the incredibly large, governed by general relativity, and the physics of the incredibly small, governed by quantum mechanics. He points his formidable mathematical intellect directly at the edge of the event horizon. According to quantum field theory, the seemingly empty vacuum of space is never truly empty. It is a chaotic, boiling soup of microscopic energy. Everywhere in the universe, pairs of virtual particles are constantly popping into existence out of nothing, existing for a fraction of a millisecond, and then immediately colliding and annihilating each other. Think of it like a cosmic bank account that briefly dips into overdraft, but the money's immediately paid back before the universe even notices the missing funds. This happens constantly, everywhere, all the time. But Hawking asks a revolutionary, dangerous question. What happens if this spontaneous particle creation occurs exactly on the razor-thin border of a black hole's event horizon? He realizes that the intense gravitational tidal forces can literally rip the particle pair apart before they have the chance to annihilate each other and pay back the debt. One particle falls helplessly into the black hole carrying negative energy. The other particle, violently separated from its partner, is violently kicked out into the universe, escaping as real, positive radiation. The implication of this microscopic quantum dance is absolutely staggering. The black hole is not completely black. It is glowing. It is leaking. It is emitting a very faint thermal glow that we now call Hawking radiation. And because Einstein's most famous equation proves that energy and mass are exactly the same thing, a black hole that is emitting energy must also be losing mass. The ultimate inescapable cosmic trap has a tiny steady leak. Over unimaginable, mind-bending stretches of time, trillions upon trillions of years, the black hole will slowly, agonizingly evaporate. As it gets smaller, it will get hotter and glow brighter. So, finally, in its dying moments, it will completely explode in a blinding, catastrophic flash of high-energy radiation, leaving absolutely nothing behind. The black hole will completely disappear from the universe. However, the mathematical confirmation that black holes eventually evaporate and disappear raised an even more troubling puzzle. Let's put the theoretical equations aside for a moment and descend into the terrifying physical reality of the monster itself. To truly understand what a black hole is, we first have to unlearn almost everything popular culture has taught us. Let's start with the name itself. The term black hole is a brilliant piece of marketing, but it is a terrible, highly misleading description of the physical object. When you hear the word hole, your brain instantly pictures a flat, two-dimensional tear in the fabric of space. You imagine a swirling whirlpool on the surface of a dark ocean or a painted black circle on a flat wall. You might think that if you flew behind it, you would see the back of the tear. But that is completely wrong. A black hole is not a flat tear. It is a perfect, seamlessly smooth, three-dimensional sphere of absolute darkness. It has a front, a back, a top, and a bottom. No matter which angle you approach it from, no matter how you fly around it, it always presents the exact same terrifying face. It is a solid shadow in the shape of a perfect globe. It has no surface you can touch, no ground you can stand on, but its spherical boundary is an absolute physical reality. There is another massive myth that we need to destroy immediately. A black hole is not a cosmic vacuum cleaner. It does not actively hunt down planets or aggressively suck up entire solar systems. Its gravity obeys the exact same classical laws of physics as any other object in the universe. Gravity is determined entirely by mass, not by the strange nature of the object. If our sun were to magically and instantly collapse into a black hole of the exact same mass right now, the Earth would not be sucked in. The gravitational pull on our planet would not change by a single fraction of a percent. The Earth would continue to orbit that black hole perfectly safely, exactly as it orbits the sun today. The only difference is that our sky would go completely dark, and all life on Earth would quickly freeze to death. A black hole is not an aggressive predator. It is a passive trap. If you respect its boundaries, it is perfectly harmless. But if you cross its critical threshold, there is no escape. You only fall in if you make the terrible mistake of getting much too close and losing your orbital speed. So, let us make that mistake. Imagine you are sitting in the cockpit of an indestructible, highly advanced spaceship. You have travelled millions of light years across the cosmos, and you're now slowly approaching a supermassive black hole at the centre of an ancient galaxy. You're preparing to cross into the unknown. What do you truly see outside your window? Because of the name, you might expect to see a quiet, empty, pitch-black void. You might expect total silence and absolute darkness. But the reality is the exact opposite. Ironically, the immediate environment just outside a feeding supermassive black hole is the brightest, most violent, and most chaotic place in the entire observable universe. Long before you reach the absolute darkness of the center, you encounter the outer rings of hell. This is the accretion disk. Picture a flattened, spinning hurricane made entirely of superheated matter, stretching for millions of miles across the vacuum of space. This disk is composed of the shredded, pulverized remains of doomed stars, crushed planets, and vast clouds of interstellar dust that wandered too close to the gravitational giant. Because of the conservation of angular momentum, this massive cloud of debris cannot simply fall straight down into the center. Instead, it is forced to spiral inward, whipping around the black hole's equator at a staggering fraction of the speed of light. The density of the material here is staggering. It is a crushing, swirling traffic jam of cosmic debris, all desperately trying to squeeze into a space that is far too small. As the material spirals closer and closer to the inner edge, the environment becomes unimaginably extreme. The gravitational friction between the rapidly spinning layers of gas is so intense that it violently rips atoms apart. The matter is violently crushed and heated to millions, sometimes billions of degrees. It completely transitions from a simple gas into a blindingly bright, violently turbulent plasma. This uppermost incredibly hot layer of the disk is known as the corona. This corona is a raging inferno of high-energy particles. The magnetic tension and the thermal energy here are so concentrated that they warp the very space around them, creating a turbulent, glowing halo that surrounds the dark heart of the beast. It acts like a cosmic nuclear reactor, but one that is infinitely more efficient than any star. The friction within the accretion disk generates so much raw energy that this swirling vortex of doom can easily outshine the combined light of every single star in its host galaxy. You're not flying into darkness. You're flying into a blinding, searing wall of X-ray radiation that would instantly vaporize any normal ship, but the sheer heat and the blinding light are only the beginning of the violence. As you pilot your ship closer to the inner edge of the disk, you encounter forces that defy human comprehension. The intense rotation of the black hole combined with the swirling electrically charged plasma of the accretion disk generates magnetic fields of unimaginable power. These magnetic field lines are violently twisted, stretched, and coiled into massive invisible springs by the insane rotation of the system. Here, the physics become utterly chaotic. These immensely powerful twisted magnetic fields act like the most powerful particle accelerators in nature. They reach down into the innermost edge of the accretion disk and grab a massive portion of the superheated plasma just milliseconds before it crosses the point of no return. Instead of letting this doomed matter fall into the absolute darkness, the magnetic fields violently compress it and blast it outward from the north and south poles of the black hole. These are the relativistic jets. They are twin focused beams of pure, destructive, highly concentrated energy shooting out into the cosmos at nearly the speed of light. They are the screams of a feeding monster. These jets are so unbelievably powerful that they can pierce through the entire width of a galaxy, stretching for millions of light years into intergalactic space. If the Earth were caught in the direct crosshairs of one of these relativistic jets, even from a distance of thousands of light years away, our entire atmosphere would be instantly stripped away. The oceans would boil into space, and the planet would be completely sterilized in a matter of seconds. You're navigating through a cosmic hurricane of blinding plasma, deadly X-rays, and planet-sterilizing beams of energy. You are witnessing the most efficient engine of destruction the universe has ever created. Now close your eyes and imagine flying straight through that blinding plasma and heading towards the absolute edge of darkness. To understand what lies at the very heart of this monster, we first have to cross into the bizarre zones where light itself is enslaved. You have miraculously survived the searing heat of the accretion disk. You have carefully navigated your indestructible ship past the planet's sterilizing relativistic jets. You're now flying closer to the absolute darkness, leaving the blinding plasma safely behind you. As you approach the black sphere, the visual distortions of the universe become incredibly intense. The starlight from the rest of the galaxy doesn't just twinkle, it stretches, smears, and violently curves around the edges of the shadow ahead of you. You're entering a highly sensitive, microscopically thin region of space known as the photon sphere. To grasp what is happening here, we must remember that light, under normal circumstances, always travels in a perfectly straight line through the vacuum of space. But Einstein's general relativity proved that extreme mass bends the very fabric of space. Because space itself is curved, the path that light must follow is also curved. Usually this bending is extremely subtle. But here, just outside the event horizon of a supermassive black hole, the gravitational pull reaches a state of terrifying perfection. The gravity is so precisely strong that it forces photons of light to bend into a perfect continuous circle. Millions of light beams are trapped in an endless, dizzying orbit around the dark center, circling the abyss exactly like planets orbiting a star. The light trapped here isn't just from local stars. It is an accumulation of light from the entire history of the universe. Some of these trapped photons have been circling the black hole for billions of years, desperately trying to escape, but forever locked in a perfect gravitational embrace. If you had an impossibly powerful telescope and looked left or right, you could theoretically see the infinite past of the entire cosmos, endlessly replaying in a brilliant, chaotic ring of trapped time. The physical consequences of this perfectly circular light path are profoundly disorienting. Imagine you could completely stop your ship and hover perfectly still exactly within this photon sphere. If you look straight ahead out of your front window, the light bouncing off the back of your own spaceship would travel all the way around the black hole. It would complete a full circle and re-enter your eyes from the front. Without a single physical mirror anywhere in the entire universe, you would be staring directly at the back of your own ship. You're caught in a cosmic hall of mirrors created entirely by the sheer, crushing force of gravity. It is an optical illusion woven into the fundamental geometry of the universe, but you cannot linger here. You push your engines further inward. As you move even closer to the dark, assuming this massive black hole is spinning, and almost all of them in the universe are spinning at furious speeds, you cross an invisible, elliptical boundary into a region called the ergosphere. The boundary of the ergosphere is shaped like a flattened pumpkin, bulging out at the equator due to the furious centrifugal force of the spin. As you cross this invisible threshold, you don't feel a sudden physical bump. There is no signpost in the vacuum. But your navigation instruments immediately scream in protest. They tell you that you are moving, accelerating in a massive circle, even though your thrusters are completely silent. You are experiencing the ultimate loss of control. The universe is dictating your motion, overriding your technology and your will. This is where the physics become deeply, fundamentally unsettling. A black hole is not just a heavy object sitting peacefully inside a container of space. It is intimately, violently woven into the very fabric of reality. When a supermassive black hole spins, it possesses an unimaginable amount of rotational energy. And because of its extreme mass, it does not just spin through space, it violently drags the very fabric of space and time along with it. Physicists call this mind-bending phenomenon frame dragging. Think of it like turning on a powerful, high-speed electric mixer inside a thick, heavy bowl of honey or thick syrup. The fluid closest to the spinning metal blades is relentlessly dragged along in a violent circle. In the ergosphere, the very fabric of space is that thick honey. The physical consequences for you, the traveller, are absolute. Once you enter the ergosphere, it is absolutely impossible to remain stationary. Even if you fire your ship's engines at maximum, absolute power in the exact opposite direction, desperately trying to stay perfectly still, you will still be dragged around the black hole. You are forced to rotate because the very geometry of the space you are occupying is rotating. You are standing on a moving cosmic treadmill and no amount of energy in the universe can stop you from moving with it. You are caught in the current of reality itself. Yet this terrifying rotational trap is not just a hazard, it is a massive, untapped source of raw power. Theoretical physicist Roger Penrose proposed a brilliant futuristic concept known as the Penrose process. He theorized that a highly advanced Type 3 civilization could deliberately fly massive structures directly into this violently rotating ergosphere. The mechanics of this energy extraction are fascinating. It relies on the strange fact that within the ergosphere, it is mathematically possible for an object to possess negative energy from the perspective of an outside observer. By splitting your ship in two and sacrificing one half to the black hole, the remaining half is violently ejected with more energy than the entire ship had when it entered. The black hole pays the difference, slowing its spin by an incredibly tiny fraction. Over millions of years, an advanced civilization could slowly, methodically drain the black hole of its rotational energy, bringing the spinning giant to a complete halt. In this theoretical scenario, the most destructive force in the universe is tamed and used as the ultimate, inexhaustible cosmic battery. The monster is harnessed to power entire galactic empires, but you are not here to harvest energy. You are here to find the absolute edge. You pilot your ship deeper through the rotating honey of the ergosphere. The optical distortions grow so severe that the universe behind you shrinks into a tiny, intensely bright blue dot, while the pitch-black shadow ahead of you expands to swallow your entire field of view. The sheer scale of the shadow is paralyzing. You are a microscopic speck of dust floating before a mountain of nothingness. The silence inside your cabin is deafening, a stark contrast to the mathematical violence raging outside your window. The boundary before you is not a physical wall. It is not made of stone or metal or plasma. It is a mathematical line drawn in the fabric of the cosmos, the ultimate point of no return. You are now hovering just inches away from the event horizon, the final gendarme of the physical universe. Just a few thousand miles deeper into the dark, the familiar laws of biology and physics are about to be violently torn apart. That catastrophic biological failure only makes sense once you understand the brutal tidal mechanics of the event horizon. You have finally reached the ultimate, uncompromising border of the observable universe. The blinding light of the accretion disk and the violent rotation of the ergosphere are now safely behind you. Directly in front of your ship lies the event horizon, the perfect, silent, spherical shadow that completely separates the known universe from the absolute unknown. Before we push you across that terrifying threshold, we must shatter another pervasive myth. Hollywood science fiction movies often portray this moment entirely wrong. They typically show a brave astronaut vanishing in a flash of light, like a cheap magic trick, or popping intact into an alternate dimension. They make it look like crossing a magical doorway. But astrophysics is infinitely more violent and unforgiving than Hollywood screenwriting. In physical truth, if you approach a typical black hole, you absolutely do not survive long enough to see what lies on the other side. To understand why, we have to look closely at a phenomenon known as tidal forces. In classical physics, the strength of a gravitational pull always decreases as the distance from the mass increases. Right now on Earth, the gravity pulling your feet is technically slightly stronger than the gravity pulling your head, simply because your feet are closer to the planet's center. But on Earth, that difference is so microscopically small that you never feel it. However, at the edge of a black hole, this subtle difference becomes infinitely, lethally magnified. Imagine you step out of your spaceship and begin to fall feet first toward the event horizon. Because the gravitational gradient near the boundary is unimaginably steep, the gravitational pull acting on the soles of your boots becomes millions of times stronger than the pull acting on the top of your helmet. You would feel your feet accelerating much faster than your head, as if you were tied to a brutal medieval torture rack. Your blood would be forcefully pulled down into your lower extremities, causing you to instantly lose consciousness long before the physical tearing even begins. The physical result on your body is catastrophic. The immense difference in gravity violently stretches you vertically with terrifying force. But that is only half of the horror. Simultaneously, the gravitational vectors acting on the left and right sides of your body are angled slightly inward toward the absolute center of the black hole. While you're violently stretched vertically, your shoulders and ribs are ruthlessly crushed inward horizontally. Your destruction is rapid. First, your bones, muscles, and tissues stretch far beyond their breaking point, snapping like dry twigs. But the forces do not stop there. As you fall closer to the horizon, the tidal forces become so overwhelmingly powerful that they easily overcome the strong electromagnetic bonds that hold your individual molecules and atoms together. Your very chemical structure is violently ripped apart. By the time your biological remains finally cross the event horizon, you are no longer a human being, nor even a recognizable collection of organic matter. You have been brutally extruded into a single, perfectly straight, infinitely thin line of individual subatomic particles, pouring into the abyss like a stream of sand. Physicists have given this gruesome, highly lethal physical process a surprisingly comical name. They call it spaghettification. Think about the sheer terror of that realization. However, your exact fate, and whether you experience this horrific spaghettification before or after crossing the boundary, depends entirely on the size of the monster you choose to visit. This brings us to another major public misconception. People often assume that all black holes are identical, standard-sized cosmic vacuum cleaners. In physical truth, the universe contains a staggering, mind-bending variety of weight classes, and the physical size of a black hole completely changes how it interacts with the matter around it. Astronomers divide these dark entities into 4 primary categories based on their mass. The first category is the stellar mass black holes. These are the most common corpses of dead stars. They typically range from 3 to 100 times the mass of our Sun. Their event horizons might only be 10 to 300 kilometers in diameter, roughly the size of a large city. Because all that mass is packed into such a tiny space, the gravitational gradient near their surface is incredibly steep. These are the ones that will violently spaghettify you long before you ever reach the event horizon. The second category is the intermediate mass black holes. These weigh anywhere from 100 to 100,000 times the mass of our Sun, with diameters stretching for thousands of kilometers. Scientists theorize they are formed by the slow merging of smaller black holes. Alternatively, they might form through the rapid, catastrophic collisions of massive stars in ancient globular clusters. For decades, these were the missing link of astrophysics. Finding these elusive middleweight entities in the vastness of space is like finding the crucial evolutionary step between a domestic cat and a tiger. The third category contains the supermassive black holes. These unimaginable titans sit at the center of almost every large galaxy. Their weight is incomprehensible, ranging from millions to tens of billions of solar masses. Because their mass is so utterly enormous, their event horizons are equally gigantic, sometimes large enough to swallow our entire solar system with room to spare. Here is the terrifying paradox of these giants. Because their event horizons are so incredibly large, the gravitational gradient at the boundary is surprisingly gentle. If you were to fall into a supermassive black hole, you would not be immediately spaghettified. You could theoretically cross the event horizon in your spaceship without feeling any physical discomfort at all. You would smoothly pass the point of no return, completely intact, doomed to be spaghettified only when you fell much deeper into the interior. The final category pushes the boundaries of our understanding, the primordial black holes. These theoretical objects were not born from dying stars. They were forged in the unimaginably dense, chaotic milliseconds immediately following the Big Bang. They could be smaller than a single grain of sand, or even smaller than an atomic nucleus, yet they could weigh as much as a giant asteroid or a large mountain. Some astrophysicists hypothesize that trillions of these microscopic primordial black holes still drift through our galaxy today. They could be the long-sought explanation for dark matter, the invisible gravitational glue holding galaxies together. Regardless of their size, whether they are microscopic relics of the dawn of time or supermassive titans ruling over galaxies, they all share the exact same terrifying anatomy. They all possess an event horizon that traps light forever, and they all hide a dark, destructive secret at their absolute center. Nevertheless, crossing the boundary is only the prelude to the greatest theoretical nightmare in physics. To truly grasp the horror of the central singularity, we must first abandon the comforting laws of nature as we know them. You have crossed the event horizon. The universe behind you has faded into a distorted, dying ember of light, and you are now falling helplessly toward the absolute center of the abyss. This is where we encounter the ultimate boundary of human comprehension. To understand what lies at the bottom, we must immediately dismantle another deeply ingrained human misconception. Our brains evolved on Earth, surrounded by solid matter. We are fundamentally wired to believe that extremely heavy things must be extremely hard, solid objects. When you're told that the mass of 10 billion suns has collapsed into the center of a black hole, your mind naturally conjures the image of a physical object. You likely imagine a tiny, unimaginably hard, infinitely dense sphere of crushed metal or tightly packed rock. You picture something you could theoretically touch if you survived the journey, but this is completely wrong. The singularity is not a physical object. It is not a solid sphere, and it has no surface. According to the mathematics of general relativity, the singularity is a conceptual topological point where the mass of the dead star has been crushed into a volume of exactly zero. Think about the profound absurdity of that statement. All the matter of a billion suns occupies absolutely zero space. Because the volume is zero, the mathematical density of that point becomes infinite. In the realm of pure mathematics, infinity is a useful and common concept. But in the realm of applied physics, infinity is a disaster. When a physics equation produces an answer of infinity, it does not mean the scientist has discovered the truth. It means the theory has catastrophically failed. It means the math divides by zero. Imagine trying to program a computer to divide a number by zero. The system completely crashes. The singularity is a fundamental crash in the operating system of the universe. It means that at the exact center of a black hole, Albert Einstein's magnificent theory of general relativity completely breaks down and stops working. At the singularity, the curvature of spacetime becomes infinite. The very concepts of up and down, before and after, completely lose their meaning. Time itself simply ceases to exist. However, the mathematical breakdown of the singularity is not what truly terrifies the scientific community. The breakdown of space and time is merely the opening act. The true nightmare, the puzzle that has sparked decades of vicious academic warfare and kept the greatest minds of our generation awake at night, is known as the black hole information paradox. This paradox represents the most violent, irreconcilable collision between the two foundational pillars of modern science: the macro-universe explained by general relativity, and the micro-universe explained by quantum mechanics. To understand the sheer magnitude of this crisis, you must first understand how quantum physicists view the universe. In the quantum realm, everything that exists is fundamentally composed of information. A physical book, an apple, a distant star, or the firing neurons in your brain, all of these are just specific, unique arrangements of quantum data. In quantum mechanics, there is one absolutely sacred, unbreakable law, a rule so fundamental that the entire architecture of modern physics rests upon it. Quantum information can never be permanently destroyed. Information can easily change its form. If you throw a heavy encyclopedia into a roaring fire, the physical book is gone. It turns into ash, heat, and smoke. But according to quantum mechanics, the fundamental information that made up that exact book is not lost. If you burn the book, the sequence of letters, the ink, the paper fibers, all of it is preserved in the subtle quantum states of the exhaust gases. The universe never forgets. It is the ultimate infallible hard drive. Every event, every particle interaction leaves an indelible quantum signature that must exist forever. If you had a hypothetical supercomputer powerful enough, you could track the exact trajectory of every single photon of heat, smoke, and ash. You could theoretically reverse engineer the chaos and perfectly reconstruct the encyclopedia. The information is always conserved in the universe. Now, introduce a black hole into this flawless quantum rule. General relativity dictates that the gravity of a black hole is so absolute that nothing, not even light, can escape the event horizon. Therefore, if you throw that same encyclopedia into a black hole, the information crosses the point of no return. According to Einstein's equations, it is trapped inside forever. For decades, physicists were relatively comfortable with this idea. The event horizon was seen as a perfect, impenetrable quarantine zone. Physicists reasoned that even if the information was inaccessible to us on the outside, it still existed somewhere in the dark interior. The universe's hard drive was simply partitioned, but no data was truly erased. Quantum mechanics remained safe, and general relativity remained unbroken. But in the 1970s, Stephen Hawking dropped a mathematical bombshell that shattered this peaceful coexistence. As we established earlier, Hawking brilliantly proved that black holes are not immortal. Because of quantum fluctuations at the event horizon, they slowly leak energy in the form of Hawking radiation. over unimaginable stretches of time, trillions upon trillions of years, the black hole will eventually evaporate entirely, shrinking down until it vanishes in a final brilliant explosion. This evaporation is the trigger for the ultimate paradox. The Hawking radiation that leaks out of the black hole is entirely thermal and completely random. It is the cosmic equivalent of static noise. Hawking proved that the particles escaping the black hole are born from the vacuum of space just outside the horizon, completely independent of the material trapped inside. The radiation is blind and amnesiac. It does not remember the encyclopedia, the stars, or the planets that the black hole consumed. It contains absolutely zero quantum information about the matter that originally fell inside. It would be nearly indestructible, capable of withstanding the immense outward pressure of the dark energy core while simultaneously holding back the crushing weight of the infalling galaxy. If gravastars are real, they look exactly like black holes from the outside. But they possess no event horizon, and they hide no singularity. Because there is no event horizon, information is never permanently trapped. The encyclopedia simply smashes into the ultra-hard outer shell and is pulverized, but its quantum data remains safely in the observable universe. A third fascinating proposition comes from the researchers of loop quantum gravity, and it introduces the concept of the Planck star. This theory focuses on the absolute limits of the microscopic world. In physics, there is a theoretical minimum limit to how small anything can be, known as the Planck length. Nothing in the universe can be smaller than this. The Planck star theory suggests that when matter falls into the abyss, it does indeed collapse into a tiny point, but it cannot be compressed infinitely. Thus, it can only be crushed down until it hits the absolute physical floor of the Planck length. Once it hits this microscopic limit, a massive quantum rebound occurs. The collapse halts, and the matter pushes back, creating an ultra-dense, incredibly tiny, but physically real object hidden deep inside the black hole. This is the Planck star. The quantum information of the encyclopedia is safely stored within the extreme density of this microscopic star. When the black hole finally evaporates billions of years later, the Planck star is exposed and it violently explodes, safely returning all the trapped information back into the cosmos. The fourth and perhaps most mind-bending solution involves the geometry of space itself, wormholes and white holes. General relativity equations allow for the possibility that a black hole is not a dead end, a bottomless pit, or a locked vault. Instead, it might be a cosmic tunnel, a violent rupture in the fabric of space and time. In this scenario, the matter and information of the encyclopedia do not get crushed into a singularity. Instead, they fall into the throat of a wormhole and are rapidly channeled through a shortcut in higher dimensional space. Eventually, they are violently spat out somewhere else. They might emerge on the opposite side of our galaxy, or perhaps in an entirely different parallel universe. The exit point of this tunnel is called a white hole. A white hole is the exact mathematical opposite of a black hole. While a black hole allows nothing to escape, a white hole allows absolutely nothing to enter. It is a one-way exit door in the universe, constantly vomiting light, matter, and radiation into space. If this theory holds true, the information paradox is solved through a cosmic backdoor. The information was never destroyed, it was simply relocated to a different zip code in the multiverse. The existence of white holes would solve many lingering cosmic mysteries. Some astrophysicists have boldly suggested that the Big Bang itself might have simply been the ultimate white hole, the explosive exit point of a colossal supermassive black hole from an older, dying parent universe. If true, every time a black hole forms in our universe, it might be birthing a completely new, baby universe on the other side of its wormhole throat. In this breathtaking vision of reality, black holes are not engines of destruction, but the cosmic seeds of creation, constantly spawning an infinite fractal tree of multiverses. The encyclopedia you threw in wouldn't be destroyed. Its information would become the foundational building blocks of a brand new reality. We have now reached the absolute core of the mystery that we introduced at the very beginning of our journey. Say, This is the paradox that keeps physicists awake in the dark. Does the encyclopedia vanish into a vibrating ball of strings? Does it crash against the hollow shell of a dark energy star? Does it bounce off a microscopic Planck floor, or does it fly out of a white hole in a distant unknown galaxy? Or, most terrifyingly, is information truly deleted, meaning our entire understanding of physics is a fragile illusion? The agonizing truth is that humanity does not yet know the answer. The information paradox remains the ultimate bloody battlefield of theoretical physics. It is the exact point where human knowledge ends and the terrifying infinite mystery of the cosmos begins. However, the mathematical confirmation of these exotic theories requires a completely new scale of observation. Let's put the theoretical mathematics aside for a moment and step back to truly comprehend the staggering physical scale of these cosmic monsters. To fully understand a black hole, you have to realize that human brains are incredibly poorly equipped to process cosmic scales. We evolved to hunt, gather, and survive in a very small terrestrial environment. We live our entire lives measuring distance in miles, time in hours and years, and weight in pounds. But out in the dark ocean of the cosmos, these human measurements become completely meaningless. To truly grasp the reality of black holes, you must violently stretch your intuition across 8 distinct dimensions of cosmic shock. The first shock is the distance ladder. To understand the sheer emptiness of space, you must walk the ladder step by step. Look at the desk or table in front of you. It is likely about 3 feet wide. Now mentally jump from that desk to the moon. That is our closest celestial neighbor, sitting about 240,000 miles away. It is a vast, intimidating emptiness. Now push further and jump to the Sun, our life-giving star situated 93 million miles away across the freezing vacuum. Keep going, past the gas giants, to the very outer edge of our solar system, reaching a distance of over 11 billion miles. To truly feel this distance, you cannot just read the numbers. You have to internalize the emptiness. When you travel the 93 million miles to the Sun, you're crossing a desert of vacuum so profound that light itself takes 8 agonizing minutes to cross it. When you reach the edge of the solar system, light from the Sun takes over 14 hours to reach you. It is a cold, lonely outpost, but the jump from there to Sagittarius A star is so vast that even light, the fastest entity in the universe, must travel continuously for 26,000 years just to cross the gap. When you finally arrive, you're confronted with an event horizon that is roughly 15 million miles across. You have mentally scaled a ladder from a 3-foot wooden desk to a 15 million mile wide sphere of perfect, absolute nothingness. The black hole reigns over a domain of darkness that is unfathomably huge. The sheer physical size of the void is paralyzing. The second and third shocks relate to the agonizing delay of light and the absolute impossibility of travel. Let us consider the pinnacle of human engineering, the Voyager space probes. They are currently hurtling away from Earth at a staggering speed of roughly 38,000 miles per hour. If we could magically point Voyager directly toward that supermassive black hole at the center of our galaxy, the journey would take hundreds of millions of years. But let us imagine that Voyager somehow survived that impossible journey and arrived safely at the event horizon. If the probe immediately fired its transmitter and sent a radio signal back to Earth at the absolute speed of light, humanity would still have to wait another 26,000 years just to hear a single beep. The communication delay alone spans the entire recorded history of human civilization many times over. This light delay creates a terrifying temporal illusion. When our most advanced telescopes capture an image of the supermassive black hole at the center of the Milky Way, we are not seeing it as it exists today. We are seeing a ghost from 26,000 years in the past. We are seeing the black hole exactly as it looked when humanity was still in the Stone Age, hunting mammoths with crude spears during the last ice age. If that black hole were to suddenly explode or vanish this very second, human civilization would not know about it for another 26 millennia. The sheer distance isolates us in a protective bubble of time. But what if we aimed for something closer? The closest known black hole to Earth is a stellar mass ghost named Gaia BH1, lurking about 1,600 light-years away. If you could somehow invent a futuristic spaceship that travelled exactly at the speed of light, it would still take you 1,600 years to reach it. That is roughly the amount of time that has passed since the fall of the Roman Empire. Furthermore, the physical isolation is absolute. We dream of interstellar travel, of warp drives and galactic empires, but the mathematics of chemical rockets are a harsh reality check. A journey of 40 billion years to the closest black hole means that the Earth will have been swallowed by our dying sun. The entire solar system will have turned to dust billions of years before our probe ever reaches its destination. Even the absolute closest monster in the dark is completely, utterly unreachable by physical means. The fourth shock is the terrifying chasm of density. To understand how densely packed a black hole is, you must apply its mathematics to our own home. Imagine a hypothetical, indestructible cosmic vice. You place the entire planet Earth inside it, including every ocean, mountain, and city. You crush it down until its escape velocity exceeds the speed of light, without losing any mass. The resulting black hole would be incredibly small. The entire planet Earth would be compressed into a sphere roughly the size of a standard glass marble, about 1 inch across. The density of this black hole marble would be measured in trillions of tons per cubic inch. To put this into a more grounded perspective, imagine holding a single teaspoon of this black hole material in the palm of your hand. And that single teaspoon would weigh billions of tons. It would be heavier than every single mountain range on Earth combined. If you dropped that teaspoon, its immense density would instantly punch a hole through the Earth's crust. It would sink effortlessly through the mantle and come to rest at the very core of the planet. It would fall like a heavy bowling ball dropping through thin air. The material is compressed so violently that the empty space normally found inside atoms, the space between the electron clouds and the nucleus, has been completely squeezed out of existence. When you compare this to the core of our Sun, where atoms are crushed together to ignite nuclear fusion, the Sun's core is just a fluffy cloud. The other extreme of the density spectrum lies intergalactic space, the emptiest void in nature, where you might find only one single solitary hydrogen atom per cubic meter. Black holes represent the absolute extreme physical limit of density in the universe. The fifth shock is the mass tremor. We previously mentioned Sagittarius A star, the supermassive titan governing our galaxy. Its weight is officially calculated at roughly 4 million times the mass of our Sun. This number is easy to say, but impossible to feel. To truly grasp this weight, imagine placing our entire massive solar system on one side of a cosmic weighing scale. The supermassive black hole wouldn't even register our presence. It is so unbelievably heavy that its gravitational anchor controls the orbital paths of billions of stars across a galactic disk, 100,000 light-years wide. Consider the orbital mechanics of the Milky Way. Our Sun, along with hundreds of billions of other stars, orbits this central behemoth. The supermassive black hole acts as the gravitational anchor for an entire galactic wheel that spans 100,000 light-years in diameter. It is the conductor of a cosmic orchestra on a scale that defies logic. If you were to somehow magically remove Sagittarius A star from the center of the galaxy right now, the intricate gravitational dance of billions of stars would be fundamentally altered. The sheer concentration of mass in one single invisible point creates a gravitational well so deep that it bends the very architecture of the galaxy around its dark heart. Yet, to compare it to the everyday world, the difference in mass between this supermassive giant and a single grain of sand on a terrestrial beach is a number so large it requires dozens of zeros to write. It is a mass so dominant that it physically warps the entire architecture of the galaxy around it. The sixth shock takes us to the opposite extreme, the primordial scale. While supermassive black holes crush the mind with their size, primordial black holes destroy human intuition with their microscopic invisibility. born in the chaotic high-pressure fraction of a second immediately following the Big Bang, a primordial black hole could be physically smaller than a single atomic nucleus. If one were floating right in front of your eyes, it would be entirely invisible to the most powerful electron microscopes. Yet packed tightly inside that microscopic subatomic point of nothingness is the exact mass and weight of Mount Everest, or a gigantic extinction-level asteroid. Imagine holding out your hand and having an invisible atom drop onto your palm, only to find that it instantly crushes your body and punches a hole straight through the crust of the Earth with the weight of the Himalayas. That is the violent, counterintuitive horror of the primordial scale. These microscopic nightmares are the ultimate cosmic booby traps, or, because they are completely invisible and emit almost no detectable radiation, they could theoretically drift freely through interstellar space or even through our own solar system entirely unnoticed. You would never see one coming. If a primordial black hole the size of an atom possessing the mass of a large asteroid were to quietly drift through the Earth, the entry and exit wounds on the planet's crust would be microscopic. However, the immense concentrated gravitational wake it left behind would trigger catastrophic, localized seismic shocks and violent geological upheavals, a mysterious path of destruction caused by an invisible, atomic-sized bullet. The seventh shock is the eternal scale of their lifespan. Humans are obsessed with time because our lives are tragically short. An 80-year lifespan is a microscopic blip in the grand cosmic calendar. Even the age of the universe, currently standing at 13.8 billion years, is nothing but a brief morning in the lifespan of a black hole. As we know, Stephen Hawking proved that black holes eventually evaporate and die by leaking thermal radiation. However, this process is agonizingly, painfully slow. For a standard stellar mass black hole, weighing just a few times more than our Sun, the total time required to completely evaporate is calculated as a 1 followed by 67 zeros in years. For a supermassive black hole, it is a 1 followed by 100 zeros. To comprehend a number like 1 followed by 67 zeros, we must discard our standard calendars. Imagine a desert containing every single grain of sand on planet Earth. Now imagine taking one single grain of sand away from that desert every billion years. The time it would take to empty the entire desert grain by grain is still a microscopic fraction of the time it takes a single black hole to evaporate. This timeline pushes physics to the absolute limits of the future. The era of stars, the time we live in now, is a fleeting spark. The true, prolonged state of the universe is the black hole era, a vast, unimaginably long epoch where these dark spheres rule a completely empty, freezing cosmos. By the time the last black hole in the universe finally evaporates and explodes, all the stars will have burned out. All the galaxies will have drifted apart and dissolved into cold dust. Black holes are the ultimate, practically eternal guardians of time. They will be the absolute last surviving structures in a cold, dead, and empty universe. The eighth and final shock is the temperature chasm. Black holes create an environment where the absolute extremes of thermodynamics exist side by side, separated only by a mathematical line. We know that the accretion disk, the swirling hurricane of shredded gas and dust orbiting the black hole, is heated by extreme gravitational friction. This plasma glows at millions of degrees, creating a cosmic inferno that easily rivals the detonation of a thermonuclear weapon. It is one of the hottest environments in the cosmos. But the profound shock occurs when you step just a fraction of an inch past the event horizon. The temperature of the black hole itself, determined by its Hawking radiation, is infinitesimally close to absolute zero, dropping to roughly minus 273 degrees Celsius. It is the coldest possible state in physics, a place where all atomic movement completely ceases. The most scorching, blinding fire in the universe and the most lethal frozen void in existence are physically touching each other, violently separated only by the sheer unyielding boundary of gravity. These 8 shocks demonstrate why black holes defy human imagination. They are not just objects, they are the absolute limits of reality itself. As we turn our gaze from the theoretical math back to the physical sky, a new generation of machines is waiting to hunt them down. To understand how humanity maps these invisible giants, we first have to explore the technological miracles of modern observational astronomy. You might be wondering about a fundamental contradiction. If the gravitational pull of a black hole is so absolute that absolutely no light can escape its event horizon, how do we know they are truly there? How do we know this isn't all just mathematical fantasy written on a university chalkboard? For decades, black holes existed purely as theoretical ghosts. Today, we observe them directly. We photograph them, we map their magnetic fields, and we even listen to the violent echoes of their collisions. However, achieving this required humanity to build machines that push the absolute, extreme limits of modern engineering. The first and most famous triumph belongs to the Event Horizon Telescope, or the Event Horizon Telescope. The sheer scale of the observational problem they faced was staggering. To photograph a supermassive black hole, you cannot look for light. You must look for the absence of light. You have to photograph the precise shadow of the event horizon silhouetted against the glowing superheated background of the accretion disk. But these objects are incredibly far away. Or, taking a picture of the black hole at the center of our galaxy is incredibly difficult. It is optically equivalent to standing in New York and trying to photograph a single golf ball sitting on the surface of the moon. No single optical telescope on Earth is large enough to achieve that level of magnification. So scientists did something incredibly audacious. The Event Horizon Telescope is not a single physical structure. It is a massive interconnected virtual lens. Scientists coordinated 8 different radio observatories scattered across the globe, placing them in the most extreme environments on Earth, from the freezing ice of the South Pole to the high oxygen-deprived mountains of Chile. By synchronizing all these telescopes with incredibly precise atomic clocks, they effectively turned the entire planet Earth into one giant unified camera lens. The amount of data this planetary camera collected was so overwhelmingly massive that it could not be transmitted over traditional networks. To understand this data volume, imagine every single movie, song, and photograph ever recorded by humanity. The Event Horizon Telescope collected more raw data in a few days than the entire digital footprint of several small nations. Because the internet is fundamentally too slow to transmit this ocean of information, they had to rely on the physical transportation of heavy metal. Scientists packed half a ton of specialized hard drives into crates, loaded them onto commercial airplanes, and physically flew them to specialized supercomputing facilities in the United States and Germany. There, massive banks of processors spent months meticulously correlating the signals, matching the atomic timestamps down to the microsecond, to finally stitch together that one single blurry photograph. The result was the historic image of the supermassive black hole in the galaxy Messier 87, a terrifying, glowing orange ring of twisted light surrounding a heart of absolute darkness. That single photograph proved Einstein right once again, mapping the exact curvature of the photon ring for all of humanity to see. But astronomy is no longer just a visual science. We don't just look at black holes, we actively listen to them. When two massive black holes spiral toward each other and violently collide, they do not emit a flash of light. The darkness simply merges with darkness. However, the sheer violence of that collision creates a massive ripple in the very fabric of space and time, like a heavy stone dropped into a quiet pond. These invisible ripples are called gravitational waves. To detect them, scientists built LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO consists of 2 massive L-shaped concrete tunnels stretching for miles across the American landscape. Inside these long vacuum tubes, powerful lasers are fired and bounced off perfectly polished mirrors. When a gravitational wave passes through the Earth, it physically stretches and squeezes the planet itself. The distance between the mirrors changes by a microscopic fraction. The precision required to detect this is mind-bending. LIGO is engineered to measure a change in distance that is thousands of times smaller than the width of a single proton. In 2015, this incredible machine detected the first ever signal, known as GW150914. It was the echo of two black holes colliding a billion light-years away. In the final fraction of a second before they merged, that invisible collision released more raw power into the vacuum than the combined light of every single shining star in the entire observable universe. LIGO successfully recorded the gravitational chirp of that monumental cataclysm, proving forever that the dark universe physically shakes and hums with gravity. To see the violent feeding frenzy occurring just outside the event horizon, we have to look in the X-ray spectrum. The superheated plasma in the accretion disk and the relativistic jets emit vast amounts of deadly X-ray radiation. Thankfully for human biology, the thick atmosphere of the Earth completely blocks X-rays from reaching the ground. But this poses a massive problem for astronomers. To solve this, NASA launched the Chandra X-ray Observatory into a high orbit around the Earth. But building an X-ray telescope is incredibly difficult. You cannot bounce an X-ray off a standard mirror. The high-energy radiation will simply blast straight through the glass. Instead, Chandra uses incredibly smooth, highly polished, nested cylindrical mirrors. The X-rays enter at a very shallow angle and skip off the surface of the mirrors, exactly like a flat stone skipping across the surface of a calm lake. This brilliant engineering allows Chandra to capture the high-energy screams of black holes tearing stars apart, mapping the invisible engines of destruction that drive the evolution of entire galaxies. While Chandra looks at the high-energy present, the James Webb Space Telescope looks deep into the cosmic past. Sporting a massive array of hexagonal, gold-coated mirrors, the James Webb Space Telescope operates in the cold darkness a million miles from Earth. The James Webb Space Telescope does not look at the event horizon directly. It looks back in time, searching the infrared spectrum for the heat signatures of the very first galaxies. Recently, the James Webb Space Telescope made a completely unexpected and highly disruptive discovery. It found what astronomers are calling little red dots. These are incredibly massive, fully formed supermassive black holes sitting in the center of ancient galaxies that existed just a few 100 million years after the Big Bang. According to our established models of physics, there simply was not enough time for these black holes to grow this incredibly large by slowly eating gas and stars. To grasp how disruptive this is, imagine walking into a kindergarten classroom and finding a fully grown 6-foot-tall adult sitting among the toddlers, claiming to be the exact same age. It defies the established laws of growth. Astrophysicists are now fiercely debating how these massive seeds formed. They might have been created by the direct catastrophic collapse of titanic gas clouds that completely bypassed the star phase. Alternatively, the early universe might have possessed a much faster mechanism for feeding black holes. The little red dots prove that the cosmos is far stranger and much more efficient at creating monsters than we ever dared to imagine. Their existence is currently forcing scientists to completely rewrite the timeline of the universe, and humanity is not stopping here. We are actively designing the next generation of machines to push the boundary even further. The Black Hole Explorer is a proposed mission that will launch a radio dish deep into space to extend the baseline of the Event Horizon Telescope far beyond the Earth. This will provide razor-sharp, high-definition images of the incredibly thin photon ring, allowing us to test the mathematics of gravity with unprecedented precision. Even more ambitious is the upcoming LISA mission. If LIGO is an observatory on Earth, LISA will turn the entire solar system into an antenna. It will consist of 3 separate satellites placed in a massive triangular formation, millions of miles apart in deep space. They will constantly shoot lasers at each other, creating a gravitational wave detector so immense that it will be able to hear the slow, low-frequency hum of supermassive black holes merging at the very edge of the observable universe. We are transforming the void of space itself into a scientific instrument. Through these technological miracles, we have successfully illuminated the darkest corners of reality. We have captured the shadows of monsters and listened to the violent drumbeat of their collisions. Every time we build a larger mirror, launch a more sensitive detector, or write a more complex algorithm, the black holes push back with deeper, more profound questions. The machines we construct are not just cameras and antennas, they are the physical manifestation of human curiosity daring to stare directly into the abyss. We are a small, fragile species living on a rock, yet we are successfully decoding the invisible mechanics of the infinite. Now, prepare your mind for the final, ultimate mystery, because the greatest secrets are still completely unsolved. That technological triumph of observing the invisible only begins to make sense when you confront the monumental questions it leaves completely unanswered. Walk into any advanced theoretical physics institute in the world, look at the complex equations scrawled across the massive chalkboards, and you will see the exact same desperate, beautiful struggle unfolding. Despite all our monumental telescopes, black holes remain the greatest unsolved puzzle in physics. We have successfully photographed their shadows and listened to the violent echoes of their collisions, but their internal mechanics remain entirely hidden. To organize this chaos, scientists divide these cosmic mysteries into three distinct layers: verified facts, working hypotheses, and the bloody battlegrounds of highly controversial theories. The first massive question revolves around the ultimate fate of information. Let us look at the verified fact. As Stephen Hawking successfully proved, black holes are not eternally dark. They emit incredibly weak thermal radiation and slowly evaporate into nothingness. Now look at the working hypothesis. Physicists strongly suspect that the quantum information of everything swallowed by the black hole is not permanently deleted. Instead, it is somehow intricately encoded in the microscopic quantum fluctuations of that escaping thermal radiation. But this leads us to the controversial battleground. How exactly is the data encoded? Is the black hole fundamentally a fuzzball of vibrating quantum strings? Is there a hidden, microscopic wormhole connected to the outside universe through quantum entanglement? This debate is not just an academic exercise. It is a vicious war for the soul of science itself. If the information is truly lost, we must throw away quantum mechanics and start from scratch. Researchers around the globe are desperately trying to weave quantum mechanics and general relativity together to solve this. They are searching for the holy grail of modern physics, a working theory of quantum gravity. Only when we have this ultimate unified theory will we finally understand how the universe's hard drive truly processes its data. The second monumental question concerns the invisible architecture of the cosmos, the dark matter connection. The verified fact is that galaxies spin incredibly fast. They spin so rapidly that they should tear themselves apart and fling their stars into the void. Yet they are held together by an enormous invisible source of gravity that we call dark matter. The working hypothesis is radical. It suggests that dark matter is not a new, undiscovered exotic particle. Instead, it is entirely made of trillions of microscopic primordial black holes, forged in the extreme pressure of the Big Bang and floating invisibly throughout the universe. This takes us to a highly controversial battleground. Do these primordial seeds physically exist right here in our own cosmic backyard? Think about the terrifying implications of this controversy. We have spent billions of dollars building massive particle accelerators, smashing atoms together deep underground in a desperate attempt to find a brand new dark matter particle. What if we have been looking in the completely wrong direction? What if the dark matter holding the Milky Way together is just a vast invisible swarm of ancient black holes? There is a raging, intense debate that a theoretical Planet 9 lurking at the very edge of our own solar system might not be a planet at all. If this controversial hypothesis holds true, it means there is an invisible, grapefruit-sized hole in reality orbiting our Sun. It is a silent neighbour formed at the dawn of time, violently pulling on distant icy asteroids in the dark. The third and most terrifying question asks what truly lies beneath the horizon. The verified fact is mathematical. Einstein's equations clearly predict a singularity. They predict a point of infinite density where all known laws of physics catastrophically break down. The working hypothesis is that nature absolutely abhors infinity. Physicists believe that quantum mechanics must eventually intervene to violently halt the collapse. Perhaps this creates a microscopic, ultra-dense, physically solid object, like a Planck star hiding at the absolute core. The controversial battleground here is the concept of the firewall. What happens in the exact millisecond you cross the event horizon? Is it a smooth, dark, painless ride into the abyss? Some physicists argue that the violent breaking of quantum entanglement at the boundary creates a blistering high-energy wall of radiation. This theoretical firewall would instantly incinerate absolutely anything falling in. This firewall paradox has completely split the scientific community in half. If the firewall exists, it violates Einstein's foundational principle of equivalence. This principle states that a person falling through the event horizon shouldn't feel anything special at the exact moment of crossing. But if the firewall doesn't exist, it violates the sacred laws of quantum mechanics. It is a vicious, seemingly unsolvable catch-22. The horizon is either a smooth trapdoor to a terrifying death, a blazing wall of cosmic fire, or a bizarre bridge to a parallel universe. And yet, despite these terrifying and seemingly insurmountable theoretical uncertainties, human consciousness is intimately tied to their violent existence. To truly understand our place in the cosmos, we must first recognize our intimate biological connection to the darkness. Human consciousness and the extreme environment of a black hole seem like complete opposites, but they are deeply intertwined by the brutal mechanics of stellar evolution. Our connection to black holes is not just philosophical, it is strictly biological and chemical. The iron atoms currently carrying oxygen through your bloodstream, and the calcium atoms fortifying your skeletal structure, were not created on Earth. They were forged billions of years ago in the superheated nuclear furnaces of ancient massive stars. When those massive stars finally exhausted their nuclear fuel, the delicate balance between gravity and outward radiation shattered. In a fraction of a second, the heavy inner core collapsed violently under its own crushing weight. It formed a stellar mass black hole, or fed a supermassive giant at the galactic center. Meanwhile, the lighter outer layers of the star were violently blasted out into the empty void in a spectacular supernova explosion. Without this catastrophic collapse, there would be no carbon for our cellular structures, no nitrogen for our DNA, and no oxygen for us to breathe. Or we owe our very existence to the exact same gravitational violence that creates the darkest objects in reality. Those blasted outer layers eventually drifted, cooled, and coalesced to form our solar system, our planet Earth, and ultimately your physical body. You are the surviving biological debris of the exact same cosmic cataclysm that birthed the black holes. When you look up at the night sky, you're not looking at a distant alien environment. You're looking at your cosmic birthplace. You're gazing at the violent nursery that sacrificed its core so that you could exist in the light. We are all children of the same gravitational collapse. This brings us to a profound realization regarding black holes and why they might be permanently deleting information from the universe, creating a paradox that keeps physicists awake at night. Humanity is a species defined entirely by the accumulation and preservation of information. The human drive to conquer death is fundamentally a drive to protect information. We build vast libraries, write massive encyclopedias, and construct sprawling digital archives specifically to defy the cold erasure of time. From the very first hunting scenes painted on ancient cave walls to the complex genetic code coiled within our DNA, we exist to protect data. The universe, in a beautiful poetic twist, seems to obey this exact same rule through the strict conservation of quantum information. But the black hole stands as the ultimate terrifying antagonist to human nature. It threatens to be the universe's ultimate unyielding eraser. The conflict between our desperate desire to remember and the black hole's terrifying capacity to forget is the central drama of modern science. If information can truly vanish without a trace inside the singularity, then the past does not guarantee the future. Cause and effect, the absolute bedrock of human logic, would be a fragile illusion. It would mean the universe is ultimately a chaotic place where history can be permanently erased. But if the information survives, escaping slowly in the cold thermal radiation over trillions of years, it means the universe remembers every single breath you take. It means the cosmos is the ultimate indestructible vault. Stephen Hawking recognized this profound philosophical struggle better than anyone. In his famous 2015 Reith Lectures, he addressed the terrifying nature of the singularity. He said, "Black holes are not as black as they are painted. They are not the eternal prisons they were once thought. If you feel you are in a black hole, don't give up. There is a way out." Hawking spent his entire life trapped in a failing biological body, fighting a disease that paralyzed his muscles while his mind roamed the cosmos. When he mathematically proved black holes evaporate, he changed our relationship with the universe. He proved that nothing is forever, not even the ultimate darkness. Even in the most extreme, terrifying gravitational trap in existence, nature finds a microscopic way to leak back into the light. Black holes are not just engines of destruction. They are dark mirrors reflecting the fragile, beautiful tenacity of human consciousness. However, the mathematical confirmation of our cosmic origin proves we are eternally bound to the abyss. The monsters hiding in the dark are not our enemies, but the absolute limits of physical reality. And you? Where in the world are you watching the sky from tonight, and what can you see above your roof? Tell us in the comments, along with the time where you are. If you love wandering through the night sky, subscribe to the channel. That's what keeps this work going. The next episode of The Edges of the Sky takes us to the James Webb Space Telescope's latest discovery, exploring a Nobel laureate's chilling warning about a completely different universe. Take care, keep the terrifying boundaries of physics in mind, and see you very soon for another journey across the sky.